Hello everyone. Welcome to the course Semiconductor Devices and Circuits, which is being taught by Professor Sanjeev Sambandhan from IC Bangalore. So this is the live problem solving session for week 2 of this course. I am Mayank Goyal and I am a research scholar in the Department of Electrical Engineering IIT Bombay. So the course is being taught by Professor Sanjeev Sambandhan, who is a professor in the Department of Instrumentation and Applied Physics at ISC Bangalore. The course plan for this week is exertion in solid state physics, which includes formation of bands, chronic Penny model, electrons and holes, crystals. This live tutorial session is happening every Sunday 6 p.m. to 8 p.m. at this Google Meet link. First, I will give you some recap of the lectures for week 2. So, these are AI generated slides, so there may be some errors in the content of the slides, but I will tell you that. so so last week we studied the Schrodinger equation and the and the states for electrons. So here this is called a potential well. So this is a 1D quantum potential well. So you can see this is a parabolic well which we studied last week as in harmonic oscillators, and this is the reference potential which is considered far from the nucleus, that is d approaches infinity. So at this point there is no forces acting on electron, so electron is free, so it's considered to be experiencing zero potential. So that is, we take that as the vacuum potential or infinity potential, which is the zero, and from there we take potential as negative. So the so if you take this quantum value and you plot Schrodinger equation states, you get some states like these. So the bottom states are called so these states which are bound by this potential well are called valence shell, valence electrons. They occupy the outermost shell, these experience the least binding force and dictate bonding interaction between atoms. So these are the electrons which are in the outermost shell, and they are like the farthest from the nucleus. And the cold levels are electrons which are deep in the well, and they are tightly bound to the nucleus. So now we talk about formation of bands through interaction. So when the distance between different nuclei is infinity, then atom A and atom B, they don't have any knowledge of each other, and the electron will occupy identical discrete energy states within both independently. So as distance reduces, these two potential profiles will interact, and the valence shell of each atom will experience the valence shell of the other atoms first, which you can see here. You can see they have started interacting. The result the result is that the so now Pauli's exclusion principle comes into play, which states that electrons are fermions, and so they which obey Fermi direct statistics, which means that no two interacting electrons can share the exact same quantum state. So when they were separate, the states were identical. So when they in, come together, then also the states will have, if the states remain identical, then the electron can stay only one state and not in the other state, which wo- which won't be possible since we have two electrons, one from each state. So what will happen is that the interacting states will get split. So to accommodate the extra electrons without violating Pauli's principle, the identical energy state levels are forced to split, so they become two different states. So this is called formation of energy bands through interaction. So what happens is that the state splitting is proportional. So bringing in a massive number of n number of atoms creates n split energy states. So if your initial number of atoms are n, so each state from each atom will split into combine to form n split energy levels. So what will happen is that outermost shells will experience significant splitting first, while innermost shells will remain largely discrete, and the splitting is so densely packed that it forms continuous bands of allowed energy states. So the energy states that are formed are continuous and very fine. So they're very the spacing between them is very fine. So we can consider them as uh, continuous. And we will also see that between certain states there will be gaps which are called forbidden gaps. So these are wide gaps that remain between the fanned bands, and these areas the Schrodinger equation does not provide any valid solution. So these are called forbidden bands or forbidden gaps. So this is how evolution is. Single atom you have when the distance is infinite, the energy states are discrete, identical quantized levels, and the electron is bound strictly to a single nucleus, entirely to a single nucleus. When two atoms start interacting, that is when they are in close proximity, then the identical levels will simply split due to Pauli's constraint, and the valence electrons will begin to share influence of both nuclei. And when you have n atoms, that is a solid. So the distance condition is lattice proximity. What will happen is finely spaced continuous bands and energy gaps. So you will have these continuous bands which are very finely spaced, and there will be forbidden gaps in between. And what will happen is that the valence electrons can delocalize across the structure. So the valence electrons can delocalize across the whole structure between different nuclei. So this is how it will look in a 1D. So the L is the length of your solid crystal. So the 1D crystal is a strictly periodic linear arrangement of identical atoms, and at crystal edges, only at the physical ends of length L does the potential return to zero. So the potential will return here to zero, which is at the infinite. So hence it will trap electrons inside the macroscopic structure. So because of this, the electrons will get trapped within this physical L length, and in the between you have these kind of potential profiles U of x, which is a periodic series of d potential wells which are separated by barriers. So now we have studied about Fermi level. So Fermi level is region below which above below which all the electrons are present at absolute zero, and the electrons are there is no electron above Fermi level at absolute zero. So this can be considered as an atomic box where electrons in lower energy states below Fermi level are tightly bound, viewing their universe strictly as a local atomic potential well, like this. And whereas the above region can be considered a crystal box, where if excited, where electron when excited becomes to higher energy, it escapes the local clutch of these barriers and becomes free. So these excited electrons now perceive the entire microscopic length as their boundary, and they are free to move throughout the solid. So for them, this is now the boundary and not this. So if we try to solve the Schrodinger equation for this true continuously curving potential profile, it will be very highly complex. So what we can do is we can consider this atomic potential as a well, and this height as a barrier. So we are substituting true potential with a mimic where they are sequence of rectangular potential wells. So we are doing this because we have already established methods for solving particle in a box equations in rectangular geometries. So this assumption leads to the chronic Poinet model. So here you have the well with length a naught and the barrier with length b naught and the lattice. So first you have region A, which is the well, which has a width of a naught. So the location is it spans from 0 to a naught, and here the potential is 0. Then you have region B barrier where width is b naught and it spans from minus b naught to 0, and the potential here is u naught. Then you have a lattice constant, which is the combined length of a naught to b naught, which is a naught plus b naught, which represents the fundamental repeating periodicity of the 1D crystal. So this region will get repeated continuously. So now we have already established the equations for the finite potential well. So the inside the well, the potential is 0. So this will be the equation which will give out the general solution as AA sine alpha x plus AB sine cos alpha x, where alpha is square root 2 me by h bar, which is always a real number. Whereas in the barrier region, we get the general solution as AB sine beta x plus BB cos beta x. Now if E is greater than U naught, then beta will be square root 2m E minus U naught by h bar, which is a real number. And so if E is greater than B naught, we know that the electron is not seeing the barrier, then the electron is above the barrier. So it is acting like a free particle. Whereas if E is less than U naught, then B will result in a complex number. So if you put a complex number in sine and cos, which will result in a real exponential, which will prove that it is the electron is tunneling as a wave through the barrier. So we just studied that. So we have this potential curved curved wells due to the interaction, which we are considering as this potential well potential rectangular potential well regions. Now there will be four boundary conditions acting on this. So two of these we have studied already, that the wave function amplitude must be identical at boundary, that it has to be continuous. So this both the wave equations should be equal. So psi is 0 should be equal to psi b 0. Similarly, the derivative must also be equal. So d psi a by dx at x equals to 0 should be equal to d psi b by dx at x equals to 0. Now we add two new conditions here, which are the rules for periodic symmetry, which is given by Bloch's theorem. So it states that when you translate the wave function by one full lattice constant, which is a naught plus b naught, so it applies a phase multiplier known as E iota k a naught plus b naught. So that means phi of x plus a naught plus b naught should be equal to psi of x plus a naught plus b naught should be equal to psi of x into e power iota k a naught plus b naught. Similarly, the derivatives will also have this property. So d psi by dx at x plus a naught plus b naught should be equal to d psi by dx at x e power into e power iota k a naught plus b naught. So when you apply all the four equations on the general solutions, all the four conditions on general solutions, what what happens is we get the equation as f minus naught e f naught e equals to cos k a naught plus b naught. Now this creates a physical constraint because f naught e is equal to cosine function. It simply means that the value for this must be between -1 to 1, which would mean that the value for f naught e should be between -1 to 1. So if for some energy the value falls between -1 to 1, it is allowed state. That means electron will possess this energy. Whereas if the energy exceeds this value, then it will result in a forbidden gap. That means the mathematical limits are broken, and therefore electron can not exist. It's impossible for electron to exist in these regions. So these result in forbidden energy gaps. So now what we do is we create a new type of diagram called EK diagram. where we plot energy against the wave factor k to reveal the permitted quantum regions, so that the electrons will take the take on energy states along the S-shaped curves, and but they will face massive energy discontinuities at integer multiples of pi by a. So in this region they are allowed, but at this point they will they will have to jump to another region because of forbidden energy gaps. So the electron hits a crystal boundary and it is forced to jump. but but what happens is that but this will also result in it will not look like a distinct discrete points, it will look like continuous. So why do discrete quantum points look like solid quantum materials? So it is an illusion of scale. So if delta k is pi by 8, it yields a where the lattice spacing is tiny, it yields a massive mathematical gap separating the bands in 10 per 10. But so but when there is crystal where delta k is pi by L, where L is a very huge number, here you can say it's in centimeter, it will yield a k very high value, which will result in an ultra tight spacing within the band. So there will be very fine gap. So because the crystal is massive compared to a single atom, the allowed states are squeezed around 10 per 8 times more tightly together than the massive gap separating the bands. To the electron, the band feels like an unbroken road. So within the band, so the spacing between within the bands is defined by the crystal size, whereas spacing across the bands is defined by the lattice size, lattice spacing. So the forbidden energy gap are huge, but within the bands within the gap are small, are very finely spaced. So they are appear continuous. Now, if you plot all the solutions from the chronic Mene model on your parabolic curve, you will see that the overall envelope will mirror the classic kinetic energy equals to h bar k square by 2m, which is given by the parabolic curve. So now what can happen is that because because we have defined parabolic conditions, so so the nature does not distinguish between arbitrary origin points in a perfectly periodic crystal. So which means we can start anywhere and it will still appear the same. So we can translate the ek diagram along the k axis, uh, and it reveals a universally continuous horizontal band of allowed energy separated by massive uncrossable gaps. So you can see it will give us such parabolic wave shapes where in the between there will be no energy states which are forbidden gaps. So this can lead from here we can create an anatomy that is valence and conduction. So this that so below the forbidden gap there's a valence band which is mostly filled. So it contains electrons occupying the outermost shells of the atom, which is tightly held by nucleus. So it cannot facilitate current. Whereas the above is conduction band, which is mostly empty, a much larger potential environment. Electrons here have escaped the direct clutch of the atom and they are roaming freely across the entire crystal. So they are free to move and hence they are easy for conducting current. But But how does an electron cross this forbidden gap and come to conduction band? So that for that one of the things is thermal excitation. So you have thermal energy which comes to this electron, excites it, and it comes staying in the conduction band, and it leaves a. So when it goes to conduction band, it leaves a vacancy behind in the valence band. So valence electron must acquire enough external energy to completely clear the forbidden gap, and once it lands in the conduction band, it is free to respond to the applied voltages. So this results in classification of materials in three categories, which are defined by the size of the forbidden gap. First is metals. So in the metals, the forbidden gap is zero. So valence band and conduction band are joined together. So which allows electrons to easily go from valence band to conduction band, and hence almost all the valence electrons are available for conduction. So electrons are easy. Then we have insulators where valence band or conduction band are very far over 2 eV. So the gap is too wide for crossing at normal temperatures. Then you have semiconductors where there's a small finite space energy gap between 0 to 2 eV. So which results in controlled and statistical jumping at room temperature. So there is some amount of a small fraction of electrons in the conduction band which is which can be quantified. So now in metals the elect so it's so in as in band diagram there is the zero energy gap, so valence band and conduction band are joined, and physically so these are atoms and these are electrons moving across. So electrons require virtually no extra energy to begin moving. At room temperature the metal is flooded with a sea of free electrons. They respond instantly to any applied voltage, which results in extreme conductivity. Whereas for semiconductors and insulators, so in insulators at room temperature, the energy available is not enough to cross into conduction band. So there are no free carriers in the conduction band and all the carriers in the valence band itself. So there is no conduction. Whereas in semiconductors, there is a very specific amount of electrons that can cross the valence gap and forbidden gap and move to conduction band. So there is a quantified amount of free carriers per volume in conduction band at room temperature, which can provide some amount of conduction. So this results in formation of electrons and holes, where conduction electron has is free negative charge, and when it leaves from one place, it creates a hole that is vacancy, which acts as a distinct positive charge carrier. So when a valence electron escapes, it leaves behind a physical vacancy, and because neighboring bound electrons can fall into this hole, the hole itself can move. This dual carrier mechanism, electrons and holes, is the foundation of all modern digital electronics. So we have the free electron and the hole. So the electron exists, moves in the conduction band, whereas hole moves in the valence band. So the electron is a physical particle moving freely through the crystal lattice, whereas the hole is a vacancy left behind, that is an empty energy state that another electron can occupy. So the charge of an electron is negative, whereas the charge of a hole is effectively positive. So you have valence band, which is mostly filled. When you get thermal energy, it crosses the forbidden gap into conduction band, which is mostly empty, resulting in a free electron in a hole. So even without light or external voltage, a pure semi-conductor at room temperature provides enough ambient heat to excite electrons across the gap. So the illusion of stillness, thermal equilibrium. So thermal equilibrium means the material is in dark with no external bias applied. So the material is in equilibrium, that is, there is no change happening in the number of electrons in the conduction band or in the valence band, but actually there is movement, events are constantly happening, whereas there is constant generation of electrons in conduction band from valence band, and then there is constant recombination, that is electrons from conduction band are falling back to valence band, but they are happening at the same rate, hence the statistics is not changing. So the net shift is zero, net current is zero. So in a pure material, every jumping electron leaves exactly one hole. Therefore, N equals to P equals to Ni, which is called intrinsic carrier concentration. For silicon at 300 Kelvin, Ni is given as 1.05 into 10 per 10 carriers per centimeter cube. So because Ni relies on ambient heat, it is highly sensitive to temperature changes. The statistical paradox of thermal excitation. So the energy gap for silicon is 1.12 eV, but the average thermal energy kT at 300 Kelvin is 0.01 electron volts. So if 0.01 electron volts is less than 1.12, how do any electrons jump? They jump because the distribution energy distribution is given by the Maxwell-Boltzmann distribution, which starts from here. The most of the energy is situated here at near 0.01 eV, most of the electrons. But as you go further, there are fewer or fewer electrons at high energy. So even at energy required to jump 1.12 eV, there are very few number of electrons present at that energy also. So and which results in this very small concentration of 10 per 10 per 10 per centimeter cube. So now we come to drift velocity. Drift. So when you apply a field, so let's say this part is at negative, this part is at positive. So the electrons will move from negative potential, negative to the positive due to the electric field, and they will drift in this direction. But so and therefore the holes will appear to move in the opposite direction because the whole movement is opposite to electron movement. So now the movement of electrons in vacuum, electron in vacuum move ideally. So pure force application F equals to ma. So the electron is continuously accelerating based on its rest mass 9.1 minus 31 kg. But in a lattice, the electron is not free moving; it is moving in a sea of atoms. So it is constantly experiencing the potential of each atom. So the electrons polarizes nearby atoms at its nose, creating temporary traps. So its analogy can be like running on a slushy ground, with each step the lattice distorts, sinking into a gravitational potential well, and the electron must constantly pull itself out to keep moving. So it has to keep jumping from one potential to another. So this is called so step one, accelerate. So electron attempts to accelerate due to electric field in the minuscule length scale. It crashes into a vibrating lattice atom or dopant effect. It loses momentum, and then it accelerates again and scatters again. So because of these constant velocity jumps and crashes, the electron does not accelerate indefinitely. Instead, it achieves a constant average speed, which is called the drift velocity. And how does a vacancy or a hole moves? So at time one, you have this. This is the vacancy. This is the we are talking about valence band here. So valence band here, there's an like position B, there's an electron. Position A is the hole vacancy. So then the electron from position B will travel to electron of position A, which will result in the electron at position A and a vacancy at position B. So you can say that the hole has moved from position A to position B. So because the electron moved left, responding to the field, the hole effectively moved right. We treat this vacancy as a positive charge particle contributing to transport. So the mechanical requirement for current. So if we have completely filled where there are no empty states, there will be zero movement because they cannot occupy the same spot. Similarly, if it is almost completely empty, there are no carriers, then again there is zero movement because there is nothing to move, which is the case in the valence band and conduction band of insulators. But in the semiconductor, we have both carriers and vacancies. So so we have partially filled states which result in rapid movement. So the current requires a combination of free carriers and empty states. So the electrons move towards positive terminal, negative charge, whereas holes with a positive charge move towards negative terminal. So the total current is electron current plus hole current. So this is the summary. And so in vacuum, we just study electron moves constantly, continuously accelerates, whereas in a crystal structure, it moves by scattering, resulting in a drift velocity. So the motion is imminent burst of speed followed by fall to low energy due to collisions with the lattice. It is a random walk heavily modified by drift and diffusion. So the drift velocity is the observable constant speed of the carrier moving through the crystal, and E is your electric field, the external force which is driving the motion. So we can proportionate both of them using a symbol mu, which is called mobility, which is a crucial parameter bridging the force, electric field, and the resulting speed. So now, so lattice scattering is using acoustic phonons. So electrons scatter of atoms vibrating due to thermal energy. So the this this results in a mobility called mu L, which is proportional to t power minus 3 by 2. So as t increases, vibrations increase and mobility decreases. Now charge impurity scattering, where electrons interact with ionized defects in the lattice. So lattice may have some defects which are ionized and the electrons will result in scatter due to the electrostatic force between the two, and this depends as mu d. The molarity is defined as mu d, which is proportional to T power 3 by 2 divided by n, where n is the impurity concentration. So as T increases, the electrons move faster, spending less time interacting with the defect. So mobility will increase. Now there's a rule called Matheson's rule, where the lowest mobility dominates. So the effective mobility is given as 1 by mu effective equals to 1 by mu L plus 1 by mu D plus 1 by mu any other effect. So you have lattice scattering, defect scattering, any other scattering. All of them will result in parallel paths for electron, and the electron will take which is the most favorable path. So hence it results in this equation. Now we come to phonon, which are quantized waves of lattice vibration. So just as electrons are moving, the lattice vibrations can also be considered moving from one lattice point to another lattice point. So phonons are particle equivalent of localized traveling waves of atomic vibration. So it's like electrons are particles behaving as waves. Phonons are waves behaving as particles. So so phonon electron interaction of phonon does not increase the electron energy significantly, but it dramatically shifts its momentum across a large distance in k space. So when a phonon interacts with an electron, it shifts the momentum of the electron, but the energy shift is very low, but energy momentum shift is very high. Now we come to effective mass. So in vacuum, force the force result is applied on the true mass, which is 9.1 times minus 7 kg. But in crystal, due to the constant effect of potentials of nuclei, the electron does not appear to have its true mass. It in fact appears to have an effective mass, which is m star. So because the electron polarizes neighboring atoms and scatters constantly, using its vacuum mass will with Newton's laws will fail. So we substitute an effective mass m star to force the simple equations to work and absorb the complex quantum interactions into a single variable. So so we don't want to complicate our maths. We want to keep our maths simple and apply the normal Newton laws on our carriers. But the quantum, so we combine all the quantum mechanical effects into a single variable m star. And how is m star defined? So, so we just studied that in EK diagrams, the electrons is on this potential is on this curves, potential curves. So m star is given as h bar square by d square e by d square, the second derivative of LNG. So the curvature of these will define the mass. So the higher the mass, there will be more reduction in effective mass. So and hence there will be high mobility, whereas low curvature will result in a high effective mass and low mobility. So now we come to hole. So now electron is on this parabola, whereas hole is on this parabola, so which is inverted. So it results in a negative second derivative, which will result in a negative mass. But what we do instead, but we cannot apply negative mass. So what we do instead is we model it as a positive charge which is moving in as in the opposite direction of the field. So there we so the negative part we shift from the mass to the charge. So now we come to macroscopic limits. So which is velocity, saturation, and high electric field. So there is zone one which is linear, where drift velocity is defined as mu e. So where typical silicon electron mobility is given as 1500 centimeter square per volt second, and hole mobility is given as 500 centimeter square per volt second at room temperatures. But at high field, when we go to very high field, electric field, we see that a saturation of current velocity happens. So where V sat is given around 10 per 5 meters per second at electric field of 10 per 6 volt per meter. So here there's linear model is breakdown. The carrier cannot travel any faster regardless of the field. Now in gallium arsenide we see a different thing. We see that there is a linear rise which is governed by mobility. Then we achieve a peak, and instead of achieving a saturation, we achieve a drop first, and then we achieve saturation. So instead of smoothly saturating, the velocity abruptly drops at high field before stabilizing a new lower saturation point. And this is called gun effect. So what happens here is which is called intervalley transfer. So you see we saw in the chronic pneumonia model that there are multiple such potential curves where electron resides. So what happens is that electron is at this valley, and when it gets at a very high, so when a electric field is applied, the electron gains energy and it moves higher in the higher. And what happens at after above a certain level, it is able to transfer from this valley to a different valley which is shallower. So since it's shallower, there is it will result in a heavier atom effective mass, which will result in lower mobility and a sudden drop in velocity. Now we come to direct versus indirect semiconductors. So in direct semiconductors, uh, like gallium arsenide, the highest point of the valence band and the lowest point of the conduction band are at the same momentum point. So the transfer of electron from valence band to conduction band or conduction band to valence band is very simple. They don't have to change the momentum. They just have to rise and drop in energy. So no translation in K space is required. But in indirect band gap like germanium or silicon, the highest point in the highest point of highest point of valence band and the lowest point of conduction band are at different momentum points. So they are not so going from valence band to conduction band requires not just a change in energy, it also requires change in momentum. So in silicon and germanium, the electron leaping across the band gap requires change in momentum also. This requires interaction of phonon to make the leap possible. So we just read that phonon interaction of electron with phonon results in change in momentum. So here we have to have a phonon interaction to make this leap between across the forbidden gap. So we have the summary is here. So lattice vibration impurities result in scattering or phonons, and quantum topography is given by the EK valley curvatures, which result in M star, conduction band and valence band. Mobility is given from scattering of electrons and is defined by q tau by n star, where tau is the scattering time. And effective mass is given as h bar square by dE square E by dk square. This results in drift velocity, which is Vd equals to mu E. Then at high electric fields, we will get saturation and gun effect. Now we come to crystals. So crystals are of generally three types: monocrystalline, polycrystalline, and amorphous. So monocrystalline is crystals where the periodic, so they have perfect periodicity, whereas amorphous have complete chaos, and polycrystalline are a combination of both. So monocrystalline have long range order, so their periodicity is across very large regions, and they are defined by constant coefficients r equals to alpha 1 a1 plus alpha 2 a2 plus alpha 3 a3, whereas amorphous have very short range order where their periodicity has negligible order range. So they have varied bond lengths and angles, and one example is glass. Then polycrystalline is have intermediate range order, so they have periodicity in smaller regions, and different regions are not in sync with each other. So there are crystalline tiles separated by amorphous grain boundaries. So each region is a crystalline, and the region between them is amorphous and called grain boundaries. So now how do we look at a lattice? So we can look through light or through electrons. So the probe's wavelength must be smaller than the structural gap it measures. So high energy. So the wavelength of light is in 400 to 700 nanometers, whereas wavelength of electrons is in 10 per minus 10 meters. So probe's wavelength must be so high energy electrons provide an extreme momentum required to shrink wavelengths down to the atomic scale, and therefore their electrons are used to look at electrons are used to look at the pro look at individual atoms. So one way to you look at atomic structures is using lattice structures is using electron diffraction, which is defined by Bragg's law. So in Bragg's law, the diffraction intensity peaks only when the wave part difference equals the integer multiple of the wavelength. So the part difference is given as 2d sine theta, which is n lambda, where d is the interplanar spacing between different lattice points. So mapping the lattice unit versus primitive cell. A unit cell is a building block that fills space entirely via translation without gaps or rotations. So it is not unique and can have multiple possible shapes, and it can contain more than one effective atom. So a unit cell is basically a cell which, if when periodically repeated, gives the entire lattice. So its shape and number of atoms is not defined, can have multiple, whereas a primitive cell is defined as the smallest possible unit cell, and it contains precisely one lattice point. The so and the calculation of that one lattice point can have, so within one primitive cell you can have partial atoms also. So where which where we use the shared node formula. So you can see here in this case, one single point is shared between four regions. So each region will have one fourth of the point. So now we come to Bravais lattices. The primary is three types of cubic Bravais lattices, which is simple cubic, body centered cubic, and face centered cubic. In simple cubic, the atoms are only at corners. So it has eight corners, and each corner we have the the atom is shared by eight eight such cubes. So we have eight corners into 1/8 atom. So one effective atom in one simple cubic cell. In body centered cubic, along other than corners, we also have one atom in the middle of the cube. So we have 8 into 1/8 plus 1 in the center. So two effective atoms. In face centered cubic, we have atom at the corners and atoms at the center of the faces. So at the each atom in the face is shared by two such cubes. So they will be counted as half atoms. So we have 8 into 1/8 plus 6 faces into half. So they will have four effective atoms. And now, how to read the position of an atom in a cubic cell is we can understand that it as two in the 2D map. So the corners will be considered as 0 or 1. So they are the floors and the roofs, the corners. Half will can be considered as midpoints of the wall, and 1/4 or 3/4 are suspended internally at midpoints between wall and the 0 and 1. So that in 3D diamond, so this is called 3D diamond structure. So silicon forms a diamond lattice, which is constructed mathematically as two interwoven FCC structures. So you have one FCC structure, and within it, at you translate at 1/4 to get the second lattice. So now we come to packing fraction, which is measuring the density inside a unit cell. So packing fraction is the volume occupied by atoms divided by total volume of unit cell. So it so atoms are physical spheres with a radius r, not mathematical points. So depending on the cell geometry, vast portions of unit cell can be empty. So packing density profoundly impacts star transport. The surface arrangement and density of these spherical barriers dictate a semiconductor's current carrying properties. So you can see a case study here of FCC. So in FCC, we have four effective atoms with radius r. So the volume of atomic volume will be 4 into 4/3 pi r cube, that is 16/3 pi r cube. And if you take the cell dimension, the diagonal atoms are touching. So the diagonal is root 4r, that is root 2a, where a is your cell edge a, which is 2 root 2r. So the volume can be calculated a cube, which is 16 root 2 r cube. So now when you divide this, the result r cube cancels out, resulting in pi by 3 root 2, which is approximately 0.74. So in an FCC crystal, 74% is solid matter and the rest is empty space. Now we come to Wigner-Seitz cell. So Wigner-Seitz cell is a primitive unit cell which results in exactly one atom, one one lattice point. So Wigner-Seitz cell is constructed. We take one point, then we connect it to its nearest atom, neighboring atom. So this is actually a wrong figure. Here it is connecting to the second nearest atom, but we have to connect it to the nearest atom. So it will only be connecting to these atoms, and then cut we connect it to nearest atom. So we cut it at the midpoints and create perpendicular bisectors and join those perpendicular bisectors, similar to here, but this is wrong. And you can see here it consists of 3 points, but and a proper it will only have 1 point, and the boundary will be defined as the Wigner side cell. So the enclosed perpendicular polygon is the Wigner side cell. So it is the most geometrically perfect definition of the space owned by a single lattice point. So now we come to real versus reciprocal space. So the real space is the actual physical space defined by the atoms and their positions. And here the space distance is measured in meters, and the spatial period is defined as a, and the geometry is defined by the physical basis vectors a1, a2, and a3. The reciprocal space is you convert the physical dimensions into momentum dimensions. So the reciprocal space is also called k space. So distance is measured in 1 by meter, and the spatial frequency is then 1 by a, and the geometry is defined by reciprocal basis vectors b1, b2, b3. So perfectly periodic arrangement of atoms in physical space transform into a distinct mathematically linked periodic crystal in frequency and momentum space. So now we come. So now in momentum space, it is defined as Brillouin zone. So if you draw a Wigner side cell inside the reciprocal space, you get something which is known as Brillouin zone, which is so it creates a facets as the integer multiples of spatial frequency, which is pi by a to pi by a. So precisely these geometrical boundaries, which is k equals to pi by a, the electron waves diffract and reflect off the zone facets. This geometrical reflection prevents electron from possessing certain energies, physically tearing the energy bands apart to create the semiconductor energy gap. So this is the physical explanation of the creation of the forbidden energy gap. So now we come back to our PPT. So now we're giving you some practice questions. So first question. In a chronic penny model, Bloch's theorem is used to establish boundary conditions across a periodic potential. Which of the following equations accurately represents the application of Bloch's theorem relating the wave functions psi a to psi b? Option A, psi a naught equals to psi b minus b naught e power iota k a naught minus b naught. Option B, psi a 0 equals to psi b minus b naught e power iota k b naught. Option C, psi a naught equals to psi b minus b naught e power iota k a naught plus b naught. Option D, psi a naught equals to psi b 0 e power iota k a naught. So you can either speak your answer or write in the chat. So the correct answer would be C. Psi A of A naught equals to psi B of minus B naught e power iota k A naught plus B naught. So Bloch theorem states that the wave function in one potential well is related to its twin well, which is translated by one period via multiplication factor. So that is, so what is the one period here? Period is A naught plus B naught. So the multiplication factor would be e power iota k A naught plus B naught. So now, and what is the gap between A naught and minus B naught? That would again will be A naught plus B naught. So the A naught and minus B naught are equivalent points separated by one period. So then, so hence the correct answer would be C. So the wave function at the boundary x equals to A naught is exactly equal to the wave function at the equivalent boundary x equal to minus B naught multiplied by e power iota k A naught plus B naught, where A naught plus B naught is the lattice constant. Hence the correct answer is C. So next question. Based on the semi-classical model of carrier transport and the EK diagram, how is the effective mass m star of a hole in the valence band defined mathematically, and why is it negative? So option A, m star equals to h bar square by d square e by dk square, and the ek relationship at the top of the valence band is an inverted parabola, making the second derivative negative. Option B, m star equals to d square e by dk square by h bar square. Holes move opposite to the electric field, requiring a negative mass to balance the equations. Option C, m star equals to h bar by de by dk. The first derivative of the energy band is negative, yielding a negative group velocity. Option D, m star equals to h bar square by de square by dk square. The presence of ionized impurities flips the sign of the oscillating force. So the correct answer would be option A. So the effective mass of a charge carrier is defined as m star equals to h bar square divided by de square by dk square. And at the top of the valence band, the ek curve takes the shape of an inverted parabola. Because the parabola is inverted, the second derivative of the energy with respect to the wave vector k, that is d square e by dk square, is a negative value. So this mathematically results in a negative vector mass for holes. But we transfer that negative sign to the charge and make the whole charge positive, so that the mass so in equations the effective mass remains positive and the charge becomes positive instead of negative. According to Matheson's rule, how do the carrier mobilities associated with acoustic lattice scattering mu L and charge impurity scattering mu D scale with absolute temperature T? Option A, mu L is proportional to T power 3 by 2 and mu D is proportional to T power minus 3 by 2. Option B, mu L is proportional to T power minus 3 by 2 and mu D proportional to 3 T bar minus mu 3 by 2. Option C, mu L is proportional to T bar 3 by 2 and mu D is proportional to T bar 3 by 2 by N. Option D, mu L is proportional to T bar minus 3 by 2 and mu D is proportional to T bar 3 by 2 by N. So the correct answer would be D. As temperature increases, lattice vibrations become more vigorous, increasing the scattering probability and causing the lattice mobility mu L to decrease proportionally to T per minus 3 by 2. Conversely, at higher temperatures, electrons have higher thermal velocities, meaning they spend less time interacting with ionized impurities, causing the ionized impurity mobility to increase proportionally to T bar 3 by 2 divided by N, where N is the impurity concentration. And Matheson's rule is used to combine these two to find the effective mobility. So, in the chronic Penny model, solving the boundary conditions yields the characteristic equation F naught E equals to cos k F naught plus B naught. What is the physical significance of the mathematically bound minus 1 less than equal to F naught E less than equal to 1 imposed on this equation? It restricts electrons to only have real wave vectors k strictly within the very first Brillouin zone. It defines the allowed and forbidden energy bands as energy values E yielding F naught E outside this range do not yield valid real wave vectors. Option C. It proves that the effective mass of the electron must alternate symmetrically between positive and negative values. Option D. It mathematically enforces the Pauli exclusion principle by limiting the absolute maximum number of electrons in a potential well to 1. So the correct answer here would be B. So the mathematical function f naught e must be equal to cos k a naught plus b naught, and it is naturally bound between -1 to 1. So energy values that cause f naught e to fall outside of this specific range cannot yield real wave vectors. So these out of bound regions physically represent forbidden energy gaps where no quantum electron states can exist. So electrons are not restricted to the very first Brillouin zone. They can have wave vectors outside the first Brillouin zone, but between the first Brillouin zone and the second Brillouin zone, there will be there will be gaps which is known as your forbidden energy gaps. Next question. For a 1D macroscopic semiconductor crystal of length L equals to 2 centimeter, an electron is localized in a continuous energy band. According to the quantum mechanical boundaries of the crystal, what is the approximate spacing delta k between adjacent allowed discrete wave vector states within the band? Option A 1.57 meter inverse. Option B 157 meter inverse. Option C 314 meter inverse. Option D 3.14 into 10 per 8 meter inverse. If you try to solve this question, don't assume an answer. It's a numerical question. You have to solve the equation. So we know that the for for a continuous energy band, the spacing between fine spacing between bands is given as delta k equals to pi by L, and L here is 2 centimeters. So the continuous looking energy bands in the EK diagram are actually made of very finely spaced distinct points due to macroscopic physical boundaries of the entire crystal. The distance between these distinct k points is given mathematically by delta k is approximately pi by L. So Given L equals to 2 centimeter, which is 0.02 meters, the theoretical spacing is delta K equals to pi by 0.02, which is 157 meter inverse. So the correct answer would be option B, 157 meter inverse. Next question. Crystalline silicon forms a diamond lattice structure which can be visualized as two interwoven face-centered cubic sublattices. For a simple standard FCC unit cell with hard sphere atoms of radius r and atomic constant A, what is the theoretical packing density? Option A pi by 6, which is 0.52. Option B root 3 pi by 8, which is 0.68. Option C pi by 3 by root 2, which is 0.42. Option D pi by 3 root 2, which is 0.74. So the correct answer will be D. So the packing density or packing fraction is the ratio of volume occupied by atoms to the total volume of the unit cell. An FCC unit cell contains an effective total of 4 atoms, which is 8 corner atoms shared by 8 cells, plus 6 space atoms shared by 2 cells. The length of the unit cell side A is related to the atomic radius r by A equals to 2 root 2 r, which you can calculate from the diagonal. So dividing the volume of the 4 atoms, which is 16 by 3 pi r cube, by the volume of the cubic cell, which is 16 by 16 root 2 r cube, we get a packing density of pi by 3 root 2, which is approximately 0.74. So the correct answer would be D, 0.74. An intrinsic silicon crystal is maintained at thermal equilibrium at 300 K in the dark if the intrinsic carrier concentration Ni is empirically determined to be 1.05 into 10 power 10 per centimeter cube. What is the exact concentration of holes, which is denoted by P, in the valence band? Option A, P equals to 0 centimeter minus 3. Option B, P equals to 5.25 into 10 power 9 per centimeter cube. Option C, P equals to 1.05 into 10 power 10 per centimeter cube. Option D, P equals to 2.10 into 10 power 10 per centimeter cube. So the correct answer would be C. So in an intrinsic or pure semiconductor thermal equilibrium, every single electron that is thermally excited across the band gap into the conduction band leaves exactly one volt behind in the valence band. Because of this detailed creation destruction balance, the total number of free electrons perfectly equals the total number of holes. Both are specifically equal to the intrinsic carrier condition Ni, which means P equals to Ni equals to 1.0 into 10 per 10 per centimeter cube. So the correct answer would be C. P equals to 1.0 into 10 per 10 per centimeter cube. The next question. At room temperature, that is 300 K, the average thermal energy KT is roughly 0.026 eV. But the band gap of silicon is much larger at Eg equals to 1.12 eV. How is it physically possible for a statistically significant number of electrons to transition into the conduction band under these specific equilibrium conditions? Option A, ambient cosmic radiation supplies the remaining energy required to breach the gap. Option B, electrons utilize quantum tunneling to bypass the energy gap entirely without requiring thermal excitation. Option C, the thermal energy is distributed with a long statistical tail, meaning a measurable fraction of electrons possess thermal energies far exceeding the KT average. Option D, the application of an intrinsic vehicle internal electric field accelerates the valence electrons into across the band gap, across the energy gap. The correct answer would be C. So the average thermal energy provided to the electrons is indeed roughly kT equals to 0.026 eV at 300 K. Again, so the K here is the Boltzmann's constant and not the K here is Boltzmann's constant, not the momentum vector K. So it's Boltzmann's constant into temperature. So when you multiply both of them, it comes out to be 0.026 eV for K equals to 300 K. However, the actual thermal energy is not uniform. It is distributed among all electrons across a broad statistical distribution, that is your Maxwell-Boltzmann distribution, that features a very large high energy tail. Because of this tail, a statistically distinct fraction of electrons inherently possess enough thermal energy to overcome the much larger 1.12 eV band gap and jump to the conduction band. Next question. In a lightly doped semiconductor sample, the carrier velocity due to acoustic phonon scattering is mathematically isolated as 1200 centimeter square per volt second, and the mobility limited strictly by ionized impurities is isolated as 600 centimeter square per volt second. Assuming no other scattering mechanisms are present, what is the effective drift mobility of the carriers? Option A 1800 centimeter square per volt second. Option B 900 centimeter square per volt second. Option C 400 centimeter square per volt second. Option D 200 centimeter square per volt second. The correct answer will be option C 400 centimeters per volt second. So the Matheson's rule states that the reciprocal of the total effective mobility is equal to the direct sum of the reciprocals of the individual scattering mobilities. That is 1 by mu effective equals to 1 by mu L plus 1 by mu D. So when we calculate this, we get 1 by mu effective equals to 1 by 1200 plus 1 by 600, which is equals to 3 by 1200, which will give us mu effective equals to 1200 by 3, that is 400 centimeter square per volt seconds. So the correct answer is option C 400 centimeter square per volt second. Next question. When an electron strongly interacts with an acoustic phonon in a semiconductor crystal lattice, what typically happens to the electron state in the context of the energy EK band diagram? Option A. The electron experiences a massive increase in its energy E, but its wave vector K remains strictly unchanged. Option B. The electron experiences a negligible change in energy E, but undergoes a very significant shift in its wave vector momentum K. Option C. The electron transitions into an amorphous transport state, losing its distinct localized definition in K space. Option D. The electron immediately drops back to the valence band, releasing a high energy photon in the process. So the correct answer is option B. An acoustic phonon acts as a localized traveling wave of atomic lattice vibration. An interaction with an acoustic phonon typically does not alter the free electron's physical energy significantly. However, it possesses a tremendous potential to drastically alter the electron's momentum. In the geometric EK diagram, this interaction perfectly corresponds to the electron moving a large distance horizontally across k-space with almost no vertical change in energy E. In solid state material science, how does a polycrystalline material structure differ from both a monocrystalline single crystal material and an amorphous material? Option A. A polycrystalline material has complete uninterrupted periodicity over infinite spaces, unlike monocrystalline materials which possess only short range order. Option B. A polycrystalline material exhibits perfectly periodic structure across within localized styles called grains, spanning microns, which are themselves separated by disordered amorphous boundaries. Option C. A polycrystalline material inherently lacks any periodic atomic arrangement at any geometric scale, behaving structurally similar to glass. Option D. A polycrystalline material contains multiple distinct elemental species arranged randomly, while monocrystalline strictly refers to pure elemental non-alloy solids. So the correct answer is B. A monocrystalline solid features complete, uninterrupted geometrical periodicity over infinite long macroscopic distances. Amorphous solids like glasses possess absolutely no geometric long-range order. Polycrystalline solids rest in between. They consist of localized perfectly crystalline tiles or grains, usually on the order of tens of microns, which are physically separated from each other by completely disordered amorphous grain boundaries. So polycrystalline are kind of combination of both monocrystalline and amorphous. So the correct answer is B. In an experimental semiconductor sample, the physical minimum of the main conduction band valley can be fitted perfectly to the energy vector parabolic relation EK equals to EC plus 2.5 into 10 power minus 38 K square in joules, where K is the wave factor in meter inverse. Given the reduced Planck's constant h bar equals to 1.05 into 10 power minus 34 joule second, what is the approximate effective mass m star of an electron drifting in this localized valley? Option A 1.1 into 10 power minus 30 kg. Option B 2.2 into 10 power minus 31 kg. Option C 4.4 into 10 power minus 31 kg. Option D 9.1 into 10 power minus 31 kg. So the correct answer will be B. So the semi-classical relation for effective mass is m star equals to h bar square divided by dE square by dk square. Given Ek equals to Ec plus 2.5 into 10 power minus 38 k square. So when we second derivative, if we calculate dE square by dk square, we get 2 into 2.5 into 10 power minus 38, which is 5 into 10 power 38 joule into meter square. Now we use h bar equals to 1.7 10 minus 34 and square it, we get 1.1025 into 10 power minus 68 joule square second square. Now dividing 1.10 into 2 power 25 into 10 power minus 68 by 5 into 10 power minus 38, we get m star equals to 2.2 into 10 power minus 31 kg. So the correct answer is option B, 2.2 into 10 power minus 31 kg. So that is all I had for today. Thank you for joining. If you have any doubts, you can ask or you may leave the chat, leave the video call.